Okay, so welcome to section 11.1, which is sequences. Okay, so definition. Oops. So a sequence, that's what we're defining. A sequence is a function whose domain, meaning the inputs, all the set of possible inputs, so whose domain is the positive integers. Denoted by a sub n, where a sub n, we do curly brackets, is some function in n. Okay, so let's note there are two types of sequences. So, number one, a finite sequence. Has n strictly less than infinite terms. So, as a sequence, a sub n can be written as a1, the first term, a sub 2, the second term, a sub 3, the third term. Remember, the input are the positive integers, namely 1, 2, 3, etc. And finally, a sub n, the final term. We also have an infinite sequence. An infinite sequence has infinitely many terms. Infinitely many terms. So that's going to be given by a sub n is equal to a sub 1, the first term, a sub 2, the second term, a sub 3, the third term, and then just dots to indicate goes on forever. Okay, so terminology. I kind of used it, but let's be formal here because I know some of you aren't even watching these videos and you're trying to glean it all from just the notes. Good luck with that. So a sub 1 is equal to the first term of the sequence. A sub 2 is equal to the second term of the sequence. A sub 3, of course, will be the third term of the sequence. All the way out to a sub n, which is going to be the nth term of the sequence. Okay, so let's note something before I do an example about where we start. So some sequences begin with a sub 0 termed the initial term. Okay, so now back to our example. So example, let's list the first 5 terms. Let's do 6 terms. 6 terms of the following sequences. Okay, so number 1, let's say we have that a sub n is defined, pardon me, as n cubed. Okay, so we have a sub n is defined by n cubed. So what that means is that the first term will be 1 cubed. The second term will be 2 cubed. The third term will be 3 cubed. The fourth term will be 4 cubed. Bring that a bit closer. The fifth term will be 5 cubed. And the sixth term, of course, will be 6 cubed. Okay, so if we cared to, we could expand this out. So I claim that the first 5 terms, A1, so A1 was 1, right? A sub 2 turns out to be 2 cubed is 8. A sub 3, no, 3 cubed is 27. A sub 4, so 4 cubed is 64. A sub 5, what is 5 cubed? It's 125. And a sub 6, well, what is 6 cubed? Well, 6 times 36. So 6 times 3, or 30, would be 180. And 6 times 6 is 36. So I claim that adding those together gives us 216. Okay, let's do another one. So subscript number 2. Hopefully that's... So now let's define a sub n as... let's do 1 over n, shall we? Okay, so we have that a sub n. Maybe I'll do a different color this time. A sub n will be 1 over n. So notice I'm highlighting the counting numbers here. So we start with 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4, then 1 over 5, then 1 over 6, and it goes on forever like that. So that is, we have that a sub 1 is equal to 1, a sub 2 is equals to 1/2, a sub 3 is equal to 1/3, a sub 4 is equal to 1/4, a sub 5, these are supposed to be subscripts, is equal to 1/5, and last but not least, a sub 6 is equal to 1 over 6. Okay, let's do another one. 1, 2, 3. Let's say we have that a sub n is equal to n over n plus 1. Okay, so I claim that a sub n is defined by n divided by n plus 1. So I claim that that will be 1 divided by 1 plus 1, comma 2 divided by 2 plus 1, comma 3 divided by 3 plus 1, comma 4 divided by, divided by 4 plus 1, comma 5 divided by 5 plus 1, comma 6 divided by 6 plus 1, comma dot dot dot. Okay, so we have that a sub 1 is going to be 1/2, 1 over 2. A sub 2 is going to be 2 over 3. A sub 3 is going to be 3 over 4. A sub 4 is going to be 4 over 5. A sub 5 is going to be 5 over 6. And a sub 6 is going to be 6 over 7. And I will be right back. Okay. So I was going to do another one, but it's kind of difficult, so I think I'll just skip example 4. Okay. So note. So when given the terms of a sequence, so when given the terms of a sequence, and by that I mean these guys and not the function itself. So when given the terms of a sequence, in order to find, we want to find the function, right? So in order to find the explicit function, let's write it that way, explicit function, f of n, where n is the counting numbers, right? We manipulate the terms, until each displays its counting number. Okay, so what do I mean by this? This is something that's better done than said. So for example, so find the explicit function, the explicit function for the terms of the sequence, terms of each sequence below. Okay, so number 1, let's say we have the terms are 1, 1/3, 1/9, 1/27, 1/81, etc. Okay, so I claim that A sub 1 is 1. I claim that A sub 2 is 1/3. I claim that A sub 3 is 1/9. I claim that A sub 4 is 1/27. I claim that A sub 5 is 1/81. So my goal is to find 1, 2, 3, 4, and 5 in these formulas. Well, I know that 1 over 81 is really 1 over 3 to the power of 4, right? And I know that 1 over 27 is really 1 over 3 to the power of 3. I know that 1 over 9 is really 1 over 3 to the power of 2. I know that 1/3, wrong color. 1/3 is really 1 over 3 to the power of 1. And then I know that 1 can be written as 1 over, wrong. Why do I keep on, holy free holy, 1 over 3 to the power, well, if I want the denominator to be 1, the power has to be 0. So I do have counting numbers, just not the correct counting numbers. So my goal is to force the numbers 1, 2, 3, and 4 in here. So I claim this is 1 over 3 to the 1 minus 1. Next, I claim that this is 1 over 3 to the 2 minus 1. Make that a bit more visible, minus 1. Okay, I claim next that this is 1 over 3 to the 3, let's zoom in, 3 minus 1, which is the same as 2. Claim that the next one will be 1 over 3 to the 4 minus 1 in the exponent. And finally, I claim that the last one will be 1 over 3 to the 5 minus 1. Okay, so I claim that A sub n will accordingly be 1 over 3 to the n minus 1. So therefore, my function, this is my function, A sub n. So therefore, I'll just say equals f sub n. Put it like that. Okay. So we found the counting numbers in each. Okay, so number 2, there's number 1. So let's say we have the sequence -1, +2, -3, +4, -5, etc. So in this case, we have that A sub 1 is -1. Then we have that A sub a sub 2 is positive 2. Then we have that a sub 3 is negative 3. Then we have that a sub 4 is positive 4. We have that a sub 5 is negative 5. So I can already see my counting numbers here. I claim that this is negative 1 times 1, which is the counting number there. I claim that this one can be thought of as negative 1 squared times 2. I claim that the next one can be thought of as negative 1 cubed. Yeah, let me be explicit here. So I'll say that this is negative 1, holy free holy, come on, to the first power times 1, which times 1, and let me write all these exponents in pink. 2, 3 times 3. I claim that the next one will be negative 1 to the fourth, because any even power is just 1, times 4. Claim that the next one will be negative 1 to the fifth times 5. So the pattern is that a sub n is going to be negative 1 to the n times n. And this is our function in n that represents a sequence. Okay. I do 2 or 3 examples here. 3. Okay, so now third time's a charm. Okay, 1, 2, 3. So we have 3. Oops, terrible bracket. Let me do this bracket better. So we have 3, 7, 11, 15, 19, etc. Okay, so in this case we have that a sub 1 is equal to 3. Then we have that a sub 2 is equal to 7. Then we have that a sub 3 is equal to 11. Then we have that a sub 4 is equal to 15. Then we have that a sub 5 is equal to 19. Okay, well, this is actually, I claim that this is 4 minus 1. I claim that this is 8 minus, sorry, that's not going to help me. Yeah, it's 8. Actually, let me not do this. Yeah, so 4 minus 1, 8 minus 1, 12 minus 1, 16 minus 1, 20 minus 1. Okay. So I claim that what we're going to get then, what is 4? 4 is 4 times 1 minus 1. What is 8? It's 4 times 2 minus 1. What is 12? Well, that's 4 times 3 minus 1. And what is 16? Well, that's 4 times 4 minus 1. What is 20? It's 4 times 5 minus 1. And you might say, well, how in the heck am I supposed to figure that out? And yes, I wouldn't expect you to figure that out on your own. It's kind of miserable. But we're going to be dealing with things that'll be easier to figure out. Just wanted to show this to you. So I claim that a sub n will be 4 times n minus 1. And that, of course, will be our function in n. Okay, so definition. Okay, so a sequence is defined recursively, and that's what we're defining, recursively, if each term is defined, or no, let me say is expressed. I don't want to use the word defined too much. Is expressed with respect to previous terms. So what does this mean? Well, first let's note that sequences given in recursive form must always always state the values for the necessary amount of terms. To move forward in the sequence. Okay, so what does this mean? So example. So find the first 6 terms. 6 terms of the following recursively defined sequences. Okay, so number 1, let's say we have that a sub n is given as twice a sub n minus 1 minus 3. And we're given that a1 is 5. Okay, so we know in general a sub n is going to be twice a sub, n minus 1, from which we're subtracting 3. And we know that a1, so we're given that a1, a sub 1, is 5. Okay, so we know a sub 1, so let's go ahead and list it. A sub 1 is 5. Well, I claim that a sub 2 is given as 2 times a sub 2 minus 1, from which I'm subtracting 3. Okay, so that's going to be 2 times what? A sub 1, from which I'm subtracting 3, which is going to be 2 times 5, from which I'm subtracting 3, which is going to be 7. Okay. So now what about a sub 3? Well, that's going to be twice a sub 3 minus 1, from which I'm subtracting 3. So that's going to be twice a sub 2, from which I'm subtracting 3. So that's going to be twice. Well, what did we get for a sub 2? We got 7 minus 3, so 14 minus 3 is 11. What is a sub 4? Well, that's going to be twice a sub 4 minus 1, from which I'm subtracting 3. So that's going to be twice 4 minus 1. That'll be a sub 3, from which I'm subtracting 3. And what was our value for a sub 3? It was 11. So this will be twice 11, from which I'm subtracting 3. So 22 minus 3 is 19. Okay, now let's come back around here. Okay, so what is a sub 5? Well, that's going to be 2 times a sub 5 minus 1, from which I'm subtracting 3. So that's going to be 2 times a sub 4, from which I'm subtracting 3, which will be 2 times, what did we get for a sub 4? We got 19, from which I'm subtracting 3. So this becomes, well, 2 times 20 would be 40, but I'm too shy, so that's 38. 38 minus 3 is going to be 35. Okay, and last but not least, I wanted the first 6, so a sub 6 is going to be 2 times a sub 6 minus 1, from which I'm subtracting 3. So that'll be 2 times a sub 5, from which I'm subtracting 3. And what do we get for a sub 5? We got 35. So this will be 2 times 35 minus 3, and 2 times 35 is 70. So minus 3 will be 67. Okay. So the first 6 terms are going to be 5, comma 7, comma 11, comma 19, comma 67, comma. Okay, so we have 5, 7, 11, 19, 35, and 67. Oops, didn't leave enough room for that. And 67, and then it goes on from there. Okay, so that is a recursively defined sequence. So number 2, let's say we have that a sub n is going to be a sub n minus 1 quantity squared plus 2, where a sub 1 is given as 2. Okay, so we know that a sub n is going to be quantity a sub n minus 1 squared plus 2. And we're given that a1, a sub 1 is 2. So I claim that a sub 2 is equal to quantity a sub 2 minus 1 squared plus 2. So I claim that that's going to be, what was quantity 2 minus 1 will be 1, so that's a sub 1 quantity squared plus 2. And we found that a sub 1 was given as being 2, so this is 2 squared plus 2, so 4 plus 2 is 6. Okay, so what is a sub 3? Well, a sub 3 is going to be the quantity a sub 3 minus 1 squared plus 2. So this is going to be the quantity 3 minus 1 will give me a subscript of 2, which we're going to square and add 2. So we found that a sub 2 had a value of 6. So we're going to take 6 and square it, which is 36. Then we're going to add 2. So I claim that that's 38. Okay, at this point it's going to become really ugly. So why did I do this? Why did I make it so ugly? Well, let's continue. So a sub 4, that's going to be quantity a sub 4 minus 1, all squared, to which we're going to add 2. So this will be, wrong color, quantity a sub 3 squared plus 2. And what did we get for a sub 3? Oh, 38. Oh boy. That's what I get for making these up on the fly. Okay, 38 squared. So off to the side, let's go ahead and do this quickly. A 3 and an 8, and a 3 and an 8, and we're going to make a grid. Then we're going to say, okay, 3 times 3 is 9, 3 times 8 is 24, 8 times 8 is 64, 3 times 8 is 24. Then we're going to do the diagonals. The first diagonal on the right sums to 4. The second diagonal sums to 14. Then we have another 14. So it's 1, 4, 4, 4. Okay, that's interesting. So this becomes 1, 4, 4, 4 plus 2 is 1, 4, 4. Just look up high. 6. Okay. Okay, you get the idea. I think I'm not going to do the first 6 terms here. I'm just going to say, well, etc. Or I can be lazy and say, okay, a sub 5 is going to be quantity a sub 5 minus 1 squared plus 2. That is, we have a sub 4 quantity squared plus 2, and I can just say, okay, well, this is 1446. So 1446 quantity squared plus 2, and just leave it like that. Similarly, a sub 6 can be written without actually evaluating it as quantity a sub 6 minus 1 quantity squared plus 2, which gives us quantity a sub, well, 6 minus 1 is 5, quantity squared plus 2. So now here comes the interesting part. So what I'm going to need to do is put brackets, and then a sub 5 was 1446 quantity squared plus 2, and brackets, to which I'm adding 2. So there we are. I could technically get rid of the brackets and add 4, but you get the idea. Hopefully. Okay, was that just number 2? Okay, so number 3. So let's say we have that a sub n is given as a sub n minus 1 plus a sub n minus 2, and we're given that a naught, or initial, is 1, and a sub 1 is also 1. So in this case, we're starting the sequence at 0, and that's perfectly fine as long as we note it. So we have that a sub n is going to be equal to a sub n minus 1 plus a sub n minus 2. So I need the two previous terms. Well, I'm given that a sub 0 is 1. I'm given that a sub 1 is also 1. So the first one I need to find is a sub 2. Okay, so that's supposedly a sub 2 minus 1 plus a sub 2 minus 2. Okay, so what's that? That's going to be a sub 2 minus 1 is 1, plus a sub 2 minus 2 is 0. Luckily, I have both of those. A sub 1 is 1, and a sub 0 is also 1. So I get 2 for a sub 2. Okay, now let's go on to a sub 3. Well, that's going to be, maybe I should have done those in blue. I don't know. Should I have done these in blue? Just to make it look visually a bit different. It seems like it's too much purple there, don't you think? Okay. Maybe that should be blue as well. Okay, so a sub 3 is going to be a sub 3 minus 1 plus a sub 3 minus 2. So that's going to be a sub 2 plus a sub 1. And we know that those are a sub 2 we just found to be 2. And a sub 1 was given as 1. So a sub 3 is 3. That's interesting. I wonder if a sub 4 will be 4. Let's see. So a sub 4 is going to be a sub 4 minus 1 plus a sub 4 minus 2. So we end up with a sub 3, to which we're adding a sub 2. Okay, so we just found out that a sub 3 is 3, and we're going to add to that a sub 2, and from the above, a sub 2 was 2. So no, we get 5, not 4. Interesting. Okay. What about a sub 5 then? A sub 5 is going to be a sub 5 minus 1 plus a sub 5 minus 2. So this is going to be a sub 4, to which I'm adding a sub 3. We have both of those. They are 5 and 3. Interesting. So we get 8. Okay. So a sub 6, 1, 2, 3, 4. I don't know if I can do it, but let's see if I can fit it here. Otherwise, I'll move it. So a sub 6 is going to be a sub 6 minus 1 plus a sub 6 minus 2. So this gives us a sub 5, to which I'm adding a sub 4. So we were given both of those. They are a sub 5 we found to be 8, and a sub 4 we found to be 5. So this gives us 13. That's a good number to end that problem on. Okay, it's a lot of work. Okay, so definition. Okay, so n factorial, that's what we're defining. Denoted by n with an exclamation point is the product of all positive integers up to and including n. That is, i.e., n factorial is going to be 1 times 2 times 3 times 4 times n. otherwise known as the product P, capital Pi, as index counts from 1 to n of index. That's one way of writing it. Okay, either way. Oh, and note, there's something very important about factorials that makes no sense except in math. 0 factorial is defined to be 1. We just define it that way, even though by definition it would be 0. We give it the definition of 1 in mathematics. Okay, so for example, so let's expand the following factorials. So expand the following factorials. Okay, so number 1. Let's say we have quantity 2n factorial. Okay, so this is quantity twice n factorial. So that's going to be, well, the first term will be 2 times 1. The second term will be 2 times 2. Oh, shoot, wrong color. Given a choice of 2. 2 times 2. The third term will be 2 times 3, etc. So what is this really? This is 2 times 4 times 6 times 8. It's all the even numbers, so it's a product of all the even numbers. Product of all of all the even numbers. Even positive integers. Okay, so number 2. What do you think 2n plus 1 will give us then, factorial? Well, let's see. If we have 2n plus 1 factorial, I claim that that'll be 2 times 1 plus 1 times 2 times 2 plus 1 times 2 times 3 plus 1. So what's that going to be? 2 plus 1 is 3. 4 plus 1 is 5. 6 plus 1 is 7. So this, if I started counting at 0 instead of 1, would have been, so note, beginning at 0, two n plus 1 factorial is equal to the product of all odd integers. Okay. Number 3. Let's say we have n factorial divided by n plus 1 factorial. Okay, so we have n factorial divided by, actually let me do the n in pink, divided by n plus 1 factorial. Okay, so what are we going to have? We're going to have 1 times 2 times 3 times the previous term, which is actually, no, times n. Just write it like that all over. We're going to have, let's see, well, n plus 1 factorial just means all positive integers up to and including. Okay, so what I'm going to do, we'll start with 1 times 2 times 3 times, well, I get to n, but then I have to go plus 1. So I need to do n plus 1. Let me do that in purple. Because it's n plus 1 factorial, it's all positive integers up to and including n. Okay, so what's going to happen then? 1 will reduce with 1, 2 will reduce with 2, 3 will reduce with 3, n will reduce with n, and all that's left over is going to be 1 over n plus 1. So let's note, why is that? If n equals to 5, say, then this means that n factorial will be 1 times 2 times 3 times 4 times 5. Okay. And this implies that n plus 1 factorial will be 1 plus 2 times 3 times 4 times 5 times 6. Because this is 5 factorial, and this is 5 plus 1, or 6 factorial. The product of all integers up to and including 6, or 5 in this case. But notice that the first 5 terms of this product are the same. So I claim that 6 factorial is really 6 times 5 factorial. So that is, i.e., id est, n plus 1 factorial is always going to be n factorial times n plus 1. So that's what we have up here. The n factorial in pink and the m plus 1 tacked on. Okay, so let's do a final one, number 4. Or that was number 3, right? Let's do 1 over n factorial. Okay, so we have 1 over n factorial. Okay, well, n factorial is just the product of all integers up to and including n. So this is going to be 1 over 1 times 2 times 3 times 4, all the way out to times n. That's all a factorial is. Well, there was one thing that I skipped, and I think I'm going to, maybe I'll go ahead and do it. So as a last example, so find the first 4 terms of the sequence that's to a sub n is given as quantity 1 plus root 5 all to the n minus the quantity 1 minus the square root of 5 all to the n divided by 2 root 5. Okay, so let's rewrite this. So A sub n is going to be, where are our n's? So this is 1 plus the square root of 5. Why is it so difficult to write the square root of 5? Or to write the number 5? Okay, all to the nth power minus quantity 1 minus the square root of 5, all to the n, divided by 2 times the square root of 5. Okay, so what would a sub 1 be? A sub 1 is going to be 1 plus root 5 to the first power minus 1 minus root 5 to the first power, all over 2 times the square root of 5. Okay, well notice to the first power the parentheses go away. So 1 minus 1 goes away, and I'm left with a sub 1 is equal to 2 root 5 in the numerator divided by 2 root 5 in the denominator. So I get that a sub 1 is actually 1. All of that just for 1. Okay, what about a sub 2? So this will be a bit more intricate. So we have quantity 1 plus the square root of 5 squared minus the quantity 1 minus the square root of 5 squared, all over 2 times the square root of 5. Okay, so now this is going to take a little bit more simplification, so let's expand the binomials. So we'll have 1 plus 2 root 5 plus 5, from which we're subtracting 1 minus 2 root 5 plus 5. After I expand the binomials, all over 2 root 5. Okay, so what can we reduce here? 1 minus 1 goes away. We also have 5 minus 5 goes away when I distribute. So what I'm left with then will be 4 root 5s divided by 2 root 5s, which leaves us with 2. Oops. 2. Okay. What about a sub 3? So that's going to be quantity 1 plus the square root of 5 cubed minus 1 minus the square root of 5 cubed, all over 2 times the square root of 5. Okay, so let's expand the binomials. So this will be 1 plus 3 root 5 plus 3 times 5 is 15 root 5. Wait, no, I don't need to the second power, it's already done. So 3 times 5 plus 5 root 5, from which I'm subtracting 1 minus 3 root 5 plus 15 minus 5 root 5, all over 2 root 5. Okay, what do we have here? 1 minus 1 goes away. 3 root 5, 15 minus 15 goes away. 5, okay, so what's left over? Oops, what am I doing? Okay, so what I see that is left over will be 3 8, a 3, 8, so 8 plus 8 is 16, root 5, all over 2 root 5. Something's wrong. What did I do? 3 and 5 is 8. 8 plus 3, 3 and 5 is 8. So that gives me 16 root 5. 2 into 16 is 8. So something 1, 2, 8. Interesting. Very interesting. Let's do the next one. I want to see what's going on here. A sub 4 is equal to 1 plus root 5 all to the 4th minus 1 minus root 5 all to the 4th all over 2 root 5. Okay. So expanding the binomials, we will have 1 plus 4 root 5 plus 6 times 5 is 30 plus 20 root 5 plus 25. 1, 3, 3, 1. 5 cubed, okay. From which I'm subtracting 1 to the 4th minus 4 root 5 plus 6 times 5 is 30 minus 4 times 5 is 20 root 5 plus 5 root 5 to the 4th is 5 squared is 25. Okay. All over 2 root 5. Okay. So let's see what we have here. So the 1 minus 1 goes away. Oops. Now let's see, we have 30 and minus 30 if I distribute. Then same thing with the 25. 25 minus 25 when I distribute. So all I have are the root 5s left over. So 4, 24, and 24 is 48. So we have 48 root 5 all over 2 root 5. Okay, so 2 goes into 48 24 times. Okay, this is interesting, but it wasn't what I thought it was going to be, but that's okay. That's okay, it'll do. That's why we did all of this. Holy free holy. Okay, well, I hope you found it interesting, and I will see you in the next section.